Okay, good morning. So we continue the lesson of integrals we started last time. So if you remember, we started with the idea of calculating the area below a curve. So we have this idea that if this is my function y equals to f of x, and then this is point A, this is point B, and then I draw these vertical lines. Okay, so you see a region which is limited by the x-axis and these two vertical lines, and of course this curve. And then we were supposed to find an idea, using that idea to be able to determine the area here. And then the one I used is a little bit different from the one in the book, so let me also explain that one. If I don't know if that is exactly the standard one or this book has chosen to use it. So if you remember, my idea was to partition this interval to sub-intervals by choosing some intermediate points. So do you remember, I call this one x1, x2, for example, x3, x4, and for consistency of notation, I also call this x0, and for example, in this case, I call this x5. And then, for example, I started drawing these lines. And in my way of doing things, I told you that, okay, concentrate on one of these sub-intervals, find the minimum value of your function on that interval. For example, for this function that you see here on this interval, the minimum value is this one. And then I told you that construct a rectangle on that minimum value. This gives you an area A1. If you want to write the formula for this area of A1, it is the width. And I told you that the width is delta x. The width of all of them are delta x, which is the length of this interval divided by 5 in this case. If you have more numbers, you need to divide by the number of numbers in the length. Okay, and then you multiply it by this height, which is f of x naught. Okay, so this is the area of this part, and then you can do the same thing for the area of the next one, taking the minimum value and construct the rectangle, and then do the same thing for that and then add them up. Okay. For some reason, the book is not concentrating on the minimum value, it's concentrating on the midpoint of each subinterval. Okay? And the whole idea is that this is a little bit more advanced topic, but if a function is integrable, it really doesn't matter which point you choose to set up your rectangles. When you increase the number of partitions and send the number of partitions to infinity, of course, different strategies give rise to different values for area 1, area 2. But when you start adding them up, it really doesn't matter which one you are choosing. Okay? Might be the only difference is that according to the behavior of the function, one strategy converges to the real value faster than another strategy. So let me explain what do I mean by that. For example, this was the strategy that I did. Let me also explain the strategy in the book. So the strategy in the book is actually based on the midpoint. So this means that instead of constructing the rectangle on the minimum value, okay, by the way, this sum that I get for the minimum value is called the lower sum. You could choose the maximum value on each case. For example, if I want to construct this rectangle on the maximum value, so I will construct this rectangle. So I am calculating something more than the area. In the previous case, my error is a little bit lower than the real area. But if I concentrate on the upper sum, meaning that I construct a rectangle on the maximum value, I am also making an error, but I am going, so the value that I get is more than the real value. If I concentrate on the upper sum, if I concentrate on the lower sum, I get something lower. But these errors approaches zero if I increase the number of partitions. Okay, so that's a lower sum, that's an upper sum. The book is using midpoint sum. Okay, so what do we mean by midpoint sum? So you concentrate on the middle point of each interval. Okay, so for example, if after doing this partition, I get this subinterval, I find the midpoint here, it means the point exactly in the middle. So let me call this midpoint of interval 1. Okay, and then it doesn't matter if this value is maximum or minimum, you actually go up and then construct your rectangle on this line. Okay, so you are making something extra, you're also ignoring some parts, but that is also your rectangle. And then you say that area 1 is just delta x as before, but f of midpoint 1. Okay, so you see that this area that I write now is different from the area if you consider the minimum value, and it is different from the area if you consider the maximum value. Okay, but my goal is that to stick to one strategy and go until the end, and then I get a sum, and then I increase the number of partition and send that partition and the number to infinity. If the function is what is called in more advanced mathematics integrable, then it is proven by mathematicians, it doesn't matter which strategy you choose, the final limit in all strategies becomes the same number. Okay, so that's the idea. So for example, here, if I want to do that, I don't start from x1, I don't start from x2, then I have to start with the middle point, which I call it M2, and then I construct my rectangle on the middle point, which is exactly this rectangle again, and area 2 is this area. Yes? So this area 2 becomes f of m2 delta x. And of course, you know that if I ask you what is m1, you will tell me that m1 is the midpoint of these two, so I add x0 to x1 and then divide it by 2. If I ask you what is m2, m2 is the midpoint between x1 and x2, so you add x1 and x2 divided by 2. It makes the calculation a little bit harder because you need to find all these x's. After you found all these x's, you need to find the midpoints, and then of course you do the calculations. Yes? If this is a standard in Swedish system, I just want you to show that in GeoGebra you can also do that. So if I switch to GeoGebra here, so for example, I realize there is some feature in GeoGebra that is called rectangle sum, and that's a good name for it because you are adding the areas of rectangles. So you start typing rectangle, yes, rectangle sum, and then you click on it, okay? And then that is something I want to show you, and that is position for rectangle start. Okay, so you have your function. So let us take the function y equals to x squared. Yes. Let me take the initial value to be 1. Let me take the final value to be 5, for example. And how many rectangles you want? Let us keep it 4, for example, for the time being. And then the position of a rectangle, if I remember correctly, it's a number between 0 and 1. So the 0 means that you start on this point, on the initial point, and then if you put it 0.5, it means that you construct your rectangle on the midpoint. If you give it 1, it means that you construct your rectangle on the right left. Let me see if I remember it correctly. For example, let me give it 0. Does it actually? Yes, it gives me a number. So what is the meaning? But unfortunately, it doesn't draw. Oh yeah, it draws something for me. Okay, so let me also show the function. What is my function? This is my function. Okay, so let me see. So you see that this number 30 that appears here is not the area, is the sum of these, the sum of the areas of these rectangles you see. And when I say 0, what does it mean? It means that when you want to construct your rectangle, construct it on the initial point of your interval, which is 1 in this case. For example, when I go to the next interval is between 2 and 3, but you see that the rectangle is constructed on the initial value. Okay, let us do it once more. I go to the next interval from 3 to 4, okay? And then you see that again, this rectangle is constructed on the value of the function at the initial point 3. Is that clear? So this is denoted by 0 here. So this number, the last number in rectangle sum, when I checked it on the web, means where it starts. For example, if you want to use the strategy in the book, this number, the last number 0 should be 0.5. So it means that the initial point is in the middle. Okay? So for example, let me see what is a good idea. So let me just do the same thing. So I would say rectangle, if we can have them on the same graph, if it is not too messy. So I would type x to the power of 2, and the initial value I still give it 1, the final value I give it 5, the number of rectangles still I give 4, but the position of the rectangle, instead of saying 0, I put 0.5, because I see some problems in the book. They're asking you to calculate this. I will recommend you, instead of doing it with hand, try to understand it manually, but I want you to be able to use GeoGebra. So is that clear for you what's happening now? You see here, in the previous case, this was the rectangle. Okay, the rectangle is constructed on the left point of the interval, this a little bit darker rectangle. And again, for the next interval, this darker rectangle is built on the initial point of the interval. But now that I order it for 0.5, you see that the first rectangle is not constructed on the initial value. It is constructed on this value. I don't know if I increase this, you can see the numbers in the middle, hopefully some, yes. So you see, this rectangle that you see here is constructed on 1.5. Yes, so you see this is 1.5. Yes, is that clear what I mean? For example, for the next one, the darker rectangle was constructed on the initial point 2, but a little bit lighter triangle. Of course, this is a bigger triangle. You see, you don't think that this is just this part, that the other part is hidden between this darker color. So if you go from 2 to 3, the midpoint is 2.5, and this bigger triangle is constructed at the midpoint. Yes, is that clear? Yes or no? And then you see that the number here is 41, the number there is 30. So they differ a lot. But the point is that if I increase the number of rectangles, even though these numbers are different, they approach to the same value, and that value is the area under the curve. Okay, so that's the idea. So that's proven by mathematicians. If you have a well-behaved function, in this case continuous function, it doesn't matter how you construct these rectangles and add them up, add the areas up. Every time you do that, it will approach to the same value, and that value is actually to be defined to be the area. So let us try to test this idea. Instead of having it 4, let me make it 10 rectangles, and then if I click this one, that is the number. Okay, and if I make this one 10,
That is the number. So you see, I don't know which one is approaching. I think in this case, because of the form of the function, it seems that the second one is approaching to the real value faster. So let me calculate this. Okay, so let me increase this to, I don't know, 100. And then I have this number. You see, apparently this number, so if you see here, this after 100 times, okay, it is reaching approximately to 40. By the way, let me calculate the exact value. So the exact value of this, the function is x squared. I told you something in passing last time about the Newton's formula. Newton's told us that if you want to do this, you find a primitive function for this one, which is this, and then your interval is from 1 to 5 in this case. You put 5 here, you put 1 here, and subtract. And I will come back to it later, but let us try to understand what is going on. If I put 5 here, it becomes that. If I put 1 here, it becomes this. When I subtract them, it becomes 124 over 3, which is how much? Which is 41, comma, for example, 3, etc. Okay? So you see that, for example, here, because of the behavior of the function, you see that if I want to reach to this number, you see that still with 10 repetition here, I am getting to a better value. Yes? So here, from the strategy I described you before, it was easier from pedagogical point, but you see that I have to do it 100 times to approach to 40.85. And the real value, as I calculated here, is 41.3. But in the midpoint strategy, I repeated only 10 times, and I'm getting even closer, 41.28, which is much closer to, it's closer to 41.3. So, but the point is that it doesn't matter if you make it infinitely many rectangles, finally they will approach to the same number. Is that clear what is going on? So of course, in this strategy, which one is more efficient? The strategy given in the book, which is midpoint strategy, is approaching faster. I don't remember, is that a theorem that always the midpoint approaches faster? And of course, you can also see it here sometimes, because the error that you are making here, so if I intuitively for these kinds of functions, you see that for my strategy that I described there, this is the amount of error that I am making. Yes? But if you use this midpoint strategy, this is, by the way, this is not your error, because you are making something more, but on the other hand, you are not. So the difference between these two is your error, which apparently is the smaller than the error that I made with this minimum rectangle. Is that clear? But the point is, as I told you, it doesn't matter if the function is continuous. Sooner or later, both of them will approach to the same number. So remember this. I think it's better to write this syntax somewhere on your notebook. So if you want to solve the problems here, for example, we can also, if you want to see, let me make it 1. So for example, when I make it 1, it means that I go for the right one. Okay, so you see, this is much more than the real value. Okay, so you can play around with this last digit. That number is a continuous number starting from 0 up to 1. 0 means the left point on the interval, 1 means the right point, and I don't know, 0.5 is the midpoint. You can play around with the numbers as you like. But remember this syntax. So there are some problems in the book. They are asking you to calculate these sums. Do one of them with hand to understand what is going on, and then learn how to use GeoGebra to calculate them. But from theoretical point of view, it is important to understand that different strategies will actually give rise to them. By the way, there is also a more important theorem. It means that you don't need to stick to the same strategy from interval to interval. You can randomly pick a point and construct your rectangle. And that's also shown that it doesn't matter which point on the interval you choose and construct your rectangle. If the function is continuous, when you calculate the limit of the sum of those areas, they will become the same number. So that is actually not that trivial at all. So how you choose the point, it doesn't matter. Okay, that is something I want you to know. Okay, so let me now officially start defining the integral. So this, do you remember last time, by being motivated by the idea of area, we realized that if I want to calculate the area that I described here, you need to calculate a limit. It is reasonable to calculate this limit, the limit of the sum of these kinds of sums. N is the number of partitions, and send n to infinity. Okay, so here this gives you the area. So last time I tried to make this definition plausible, and if you remember, I told you that even though it seems not possible to do it infinitely many times, I gave you a very simple example so that we were able to calculate this limit for calculating the area, even though we knew about that area. Okay. But let me give you another problem that this limit somehow becomes important. So now assume that you have a moving particle. So you have a moving particle, say it's moving on the x-axis on one dimension. And I will assume that it always goes to the right. Okay. So if the speed of this particle is, so I don't speak about velocity because I'm assuming that it is going on to the right all the time. So I will talk about speed rather than velocity. So if you have this particle moving to the right, and assume that this particle, the speed of this particle is constant, and the speed is always 2 meters per second, and I wait for, I don't know, 10 seconds, and then I ask you what is the distance traveled by this object. So the calculation is simple. So you just multiply these two, yes? And the answer, for example, becomes 20 meters. So if the speed of the moving object is constant all the time, and if you want to see how much the particle moves in a time interval, you just multiply the length of the time interval by the speed. Yes? But let me ask you this question. What if the speed is changing? For example, say I have a particle moving like this. The speed of the particle at instant t, here the speed of the particle at any instant is constant too. Okay, but let us assume that this is not the case. I have this, and then let me say it is 2 times t. So for example, the starting speed or the initial speed is 0, because when you start, assume that you press the watch, and then the time is 0 there, so it means the speed when it starts is 0. Some force is acting on it for some reason, and then it will accelerate. For example, if I ask you what is the speed of my particle 1 second later, you will tell me it is 2 meters per second. That's because you replace t with 1. If I ask you what is the speed of my particle 2 seconds later, you will say it is 2 times 2, which is 4. Yes? Okay, but now the question is the same. Let us say I wait 10 seconds. How much the particle has traveled? Okay? So this is what we want to ask again. At least I want you to understand that the problem is not as simple as before. Yes? And in general, what I want to do, I want to solve this problem. Okay, so I want to solve this problem. For example, v of t, here I mentioned 2t, I could mention t squared, I could mention any function of t, so let me write it f of t. Okay, and say that I do this experiment from the time a to time b. Yes, and then I want to know what is the distance traveled by the particle. So this is the general setup. Okay, here I gave you one simple example. V of t is 2t, t is 10 seconds. I want to calculate the distance traveled. Here I am saying that let us assume that v of t is not 2t, any function of t, and the initial time is a, and the final time is b, and then we want to know what is the distance traveled. I don't want to solve this problem, but I want you to understand that if you want to answer this question, which is a totally different question than finding the area, it gives rise to the same idea of that limit again. Okay, so how do you, for example, see the problem? How do you do that? So what you do, for example, let me consider this case. This is the t-axis, the time. So let me write time here. And then what you start, the time, the initial time is A, the final time is B. And the speed of the particle is not moving in 2 dimensions, the particle is moving in 1 dimension, okay? And then you want to find the distance traveled by that. So what do you do? Because you know that you cannot say v of t multiplied by the time interval. So what is the length of the interval? This is the time that has passed from the initial time to the final time. But I hope that you agree that you cannot multiply this by f of t and say that is the distance traveled because the speed is changing. So what we do, the idea is exactly the same as we did for the area. For example, we start partitioning this to sub-intervals. Okay, so let us say this is t1, this is t2, and this is t3. For consistency of notations, again, let me call this t node, and let me call, in this case, t4. Okay? And then what I do, I will approximate the distance traveled by the particle on this shorter interval rather than this longer interval. By doing some approximation, what do I mean? Assume that your particle is here. This particle has some speed when it is here at this moment of time. Okay? I will take that value and put it in my function, which I get f of a. So if someone asks you what is f of a, you will tell me that f of a is the speed of the particle at this instant of time. And then this, I call it delta t. Okay, the increment in time. And I'm assuming that all of them are the same. So I ask you, what do you think? What is a good interpretation of this quantity? What is the interpretation of that? So f of a, you put ta, it gives you the speed when time is a. And then you multiply it by the time interval here. Of course, it gives you a distance, because this is a speed, this is time, speed times time multiplied by time gives you a distance. But how can you interpret this distance? Can I make sure that this is the distance traveled by my particle from this time to that time exactly? No, it is not exactly that one, because this is the speed of the particle exactly at this moment. A little bit later, the speed of the particle is different because the speed depends on which time we're looking at. But the point is that this is an approximation of how much my particle has traveled during this delta. How much this approximation is good or bad depends on the speed of my particle and how long this time interval is. But I hope that intuitively you agree with me. If I make this time interval shorter, this quantity get closer to what is real. Yes? Because the particle does not have enough time to change speed dramatically. Yes? Is that clear? So if I make the time interval shorter and shorter, I will not give that much chance to my particle to be able to change the speed. So this quantity is the first distance traveled on the first interval. Okay? But d2, instead of a, let me put t node. But for t2, what can I write? I can write f of t1 times delta t. Yes? If I ask you what is this quantity, you will tell me that when my particle reaches here, at this moment of time, the speed is f of t1, and I multiply it by the time interval, it gives me the distance traveled by my particle on this interval if the speed of the particle all the time is equal to the speed of the particle at initial time t1, which of course is not the real case, but this is an approximation to the real case. And then you continue the same thing. For example, instead of having four intervals, let us assuming that I have n intervals. So that's the same thing. It becomes f of tn minus 1 delta t. And if I add these distances, so d1 plus d2 up to dn, I add them up and I write the sigma notation for it, so it becomes f of ti delta t, I goes from 1 to n minus 4. If I ask you, what is this quantity that I calculated? You will tell me this is the approximate distance traveled by my particle during this time interval. Yes, is that clear? But hopefully you agree with me, if I increase the number of partitions, then I am making my error of the distance traveled by my particle less and less. Okay, and exactly the same story. So if you want to find d, you take this sum and take the limit and send n to infinity. Okay, so tell me, is the idea clear for you? So what I do actually, I have a particle whose speed is changing. I start dividing my longer interval, which I am interested in, to shorter intervals, and approximate the distance traveled by my particle on each subinterval, assuming that the speed of my particle all the way is equal to the speed of the particle at the initial time, which of course is not true, because even this interval is short, the speed of the particle is changing. Okay? But the point is that if I make the time interval shorter and shorter, the particle does not have enough time to change its speed very much. Even if the particle is moving with the speed of light, I can make the time interval, I don't know, a billionth of a second or even less. So even for a photon, which is going very fast, if you make the time interval very, very short, you will not give that much chance for the particle to change its speed. Intuitively, I want you to understand that when I increase the number of partition, meaning that if I decrease the value of delta t, then this sum becomes a better and better approximation to the distance traveled by the particle. Is that understandable or not? Okay, and then if you look at the structure of this limit, when I am calculating the distance, which is in the physical world, and this structure of that limit when I was calculating the area, which is a mathematical problem, I hope that you see that there are very similarities except the final. By the way, when I send n to infinity, there is no difference between n minus 1 and n. Okay? So these structures are very, very similar. And that's exactly the same idea. You see this limit started appearing in mathematics quite a lot. Mathematics, physics, application, and science. Okay. So whenever this happens, exactly like the limit when we were dealing with derivatives, that limit appeared a lot in mathematics. Whenever this happens, mathematicians start giving this limit a name and try to study its properties. So that was the motivation behind the notion of an integral. Is that clear? So we had two examples, one example from the physics and one example from geometry. Here we wanted to calculate the area. Here we wanted to calculate the total distance traveled by a moving particle with non-uniform speed. And then we realized that both of them gave rise to the same limit structure. And whenever this happens, of course, you can have a lot of examples of this kind. And then whenever this happens, it is in mathematics, people try to give it a name and try to explore its properties. The name mathematicians gave to this limit is integral. Yes? So let me just write the definition. So let f be a function that is continuous Of course, in higher mathematics, you can also discuss about if what is happening if my function is not continuous, but that's not part of your lesson. So let f be a function that is continuous on the interval a less than or equal to x less than or equal to b. This is the adjective that we usually use, but this is not in your book because you have only one type of integrals. So the definite integral of f on this interval is denoted by this symbol. And is defined by exactly as we did before. So integral from a to b f of x dx is the limit sigma I goes from 1 to n f of xi delta x n goes to infinity, where delta x is defined to be b minus a over n, and n is the number of partitions. Of the integral. Okay. So, yes?
Why did you use a code equals?
What?
Why did you use a code equals?
I'm defining delta x to be this.
Why can't
Yes.
you say that it's equal to?
Yeah, you can write the equal to. Doesn't matter that much. Okay, so one thing I want you to know, roughly speaking, you can say that, okay, by the explanations we did before, you can just say that this is the integral, yes? And there are some names I want you to know. This function that appears here is called the integrand. Yes. This is the integral sign, which is, by the way, a stretched S. So some old books still write S. Why S is a good name? Yeah, because that's a sum. Yeah, so you're adding something. So this is a good idea back in the back of your head when you're calculating integrals, or you're actually calculating an infinite sum. Yes. And then this is called the lower limit, and this is called the upper limit. So let me not mess this. So A and B are limits. A, the lower limit, B is the upper limit. And this one is a little bit more tricky. We can give two rules for this dx. First of all, this dx, you can imagine this is the same. Of course, you see that when I send n to infinity, delta x becomes 0. But that's the whole point. This is the infinitesimal calculus. So if I say that dx is the limit of delta x when n goes to infinity, you will tell me that this limit is 0, and you are right. So dx is not 0. Okay, but you can imagine dx is very small delta x. I know this is not a good explanation, but this is how it is. Even in the book there doesn't point anything to it. And that's called differential of x. Okay? But for you, dx means x is your variable. Remember, whenever you see dx, it is emphasizing that x is your variable. Why this is important? Because sometimes you can have a function f of x to be tx, and then you have two letters involved. They can write dt, they are emphasizing that t is variable. They can write dx, emphasizing that x is variable, or something like that. So for the time being, this is a good thing for you to realize it in that way. Whenever you see d, the letter coming after d is pointing which variable you're supposed to consider the variable of integration. Okay? But I want you to understand, even though we started from physics or geometry, but this integral is an abstract concept. It's just this sum, without telling you that much. If you want to calculate, if you calculate this limit, you get a number. That number is called the integral of your function from a to b. Okay? Now let me ask you one question. I want to see if you understand this idea or not. Do you think that this integral can be negative? Yes or no?
The sum.
No, I'm asking, the question is clear. Can the value of one possible, can you give me is it possible to have a negative value for one integral, for a given integral, or not? The reason that I'm asking you, because if you just think that area is integral, you will say no, because area cannot be negative. But I want you to understand, even though the motivation behind defining the integral is coming from the area, but integral is not the area. Integral is this sum, and this sum can be negative. Can you see how, for example? Let me ask you one question. Can delta x be negative? No, delta x is defined in that way. B minus a, b is the number on the right, a is the number on the left. So b minus a is positive, n is positive. So there is no way for delta x to be negative. Delta x is always positive, so there is no way for doing that. But can f of x be negative? Yes? Yes, it is in principle. If I give you this function, if this is a and this is b, and the function goes below the x-axis rather than above the x-axis, so it doesn't matter how do you this partition and how do you make these rectangles. It doesn't matter. For every value of x on this interval, the value of the function is negative. Is that clear? So if the value of the function is negative always, and delta x is positive always, When I multiply them, it becomes a negative number, and I have a bunch of negative numbers, I am adding them up, and I will get a negative number. Is that clear? So the integral is not always positive. Yes? It might be negative. Is that clear or not? Yes or no? Okay. But now, let us try to explore something about this definition. What do you think will happen if these two limits are the same? So I have the integral of f of x dx from a to a itself. I want you to understand this definition a little bit better, but don't worry, this definition is harder than the level of this course. So I want you to have a good understanding about it without going to that much detail about it. So if a and b are the same, can you predict what will happen for this limit? Calculating this limit, I told you, is very hard usually, but some particular cases we can immediately answer. What happens? Yes?
If a and b is the same, then the delta x is 0.
Yes?
So the answer will be 0.
0, yes? So if b and a are the same, so delta x becomes 0, and when I put delta x 0, independent of which, because you see this delta x, the way that we define it does not depend on the index. So when delta x is 0, it is 0 for all the terms, so it means that I have a bunch of zeros adding up, it becomes 0. When I calculate the limit, it becomes 0. Intuitively is correct. So if you have integral from a to a, f of x dx is equal to 0. By the way, from the area interpretation, that's also somehow understandable, because what do? You draw the graph, but you start from A, but end up with A, and you are interested to calculate the area. So what's the area? So if I go up to B, of course, this is my area. If I make B closer and closer to A, the area becomes smaller and smaller, and finally, if B is A itself, nothing is left from the area. Okay, let me ask you one question. What do you think if someone calculates this integral, okay, and someone calculates this integral? Do you think there is a relation between these two? So here, I can give this a name, g of x, if you want to. So someone puts, I don't know, x here, someone puts 2x here. Do you think there is a relation between these two integrals? Yes? Why?
Well, I mean, in the case what you just said, if x equals y, then
No. Just don't consider case by case. Any function. Yes?
I mean, the sum is multiplied by 2.
Yeah, the y value is multiplied by 2.
No, yeah. So no. Just refer to the definition. If this is x, f of x appears here.
Yeah, I mean,
If that is 2f of x, what appears here? 2f of x. But 2 is a constant. It means that you are multiplying each one of these numbers by 2. So you can pull that 2 out. And then when you pull 2 out, 2 goes behind. Okay? So if I ask you to calculate the limit from a to b of 2f of x dx, you calculate the limit of sigma I goes from 1 to n. You put 2f of x here, and then 2f of xi here, and then delta x. And then send n to infinity. So then what happens? This becomes the limit. What happens? 2 goes behind the sigma. Is that understandable? Because if you write 2f of x1 plus 2 of fx2, this is one way of writing. One way is to factor 2 out, yes? So I can factor a 2 out. The 2 is a constant. It goes behind the limit. This becomes 2 times the limit. N goes to infinity. Sigma f of xi delta x. But if I ask you what is this part without looking at 2, this is exactly the integral of f. And then you have a constant there, so this becomes 2 integral from a to b f of x dx. Yes? Yes or no? Is that clear? So what do you think will happen if I put a constant here? Let me just put a constant here. So how these integrals are related? So integral from a to b, c, which is a constant, multiplied by f of x dx. If someone asks you to calculate this integral, what do? If you want, you can put c outside, forget about c, and calculate this integral, and then multiply it by c. Yes? Understandable? Okay, what is your prediction for this? If someone gives you two functions added together, and then you want to calculate the integral of this new function that you form by adding them, do you think there is a connection between the integral of this new function and the integrals of this function and that function separately? I mean, even though this is a hard definition, but sometimes it is helpful to understand things. So do you understand what is the connection now? Okay, can you help me to write this? If I ask you how should I write this integral, what do you say? What do you say? Every integral is a limit. So I would write the limit. I would write my sigma, I goes from 1 to n goes to infinity. But I want you to help me. What should I write instead of f of xi this time? What should I write in front of sigma? What? F of xi plus g of xi. Yes? So this becomes f of xi plus g of xi. And then multiplied by delta x. But what happens now? I can multiply this delta x in. So this becomes the limit of sigma I goes from 1 to n, f of xi delta x plus g of xi delta x. But then I have a sum of two, I can decompose it to two sums. Yes? So I can copy and paste the limit. Of course, n goes to infinity. I can copy and paste the limit, and then I break that sigma into two sigmas. Sigma of the first part plus the sigma of the second part. Okay, is that understandable? And then I have a limit of the sum. I can break the limit now. So I can write the limit, if the limits of course exist, the limit of the first one plus the limit of the second one. Yes? So you see, this is, I just use the definition, and then I use simple algebra by multiplying this number in. Then I decomposed my sigma into two sigmas. Then I decompose my limit into the sum of limits. But what can I write instead of first one? What can I write? It becomes integral from a to b f of x dx plus integral from a to b g of x dx. Okay? So this means that the integral from a to b f of x plus g of x can be decomposed into the sum of two integrals. Okay? We will discuss about these properties later in Math 4 without the proof. But the proof is, by the way, you see it is possible. So many of you actually answered the question, so it is understandable. I just want to give you some ideas how to work with this, even though this is bad from practical point of view to calculate the values, but it is good for proving theorems. So for example, here we were able to show that the integral of the sum is equal to the sum of integrals. Okay, I didn't calculate this limit, but I used the definition to prove a theorem. And that is the benefit of having this definition in hand. This is somehow the idea. Okay, but let me ask you one question. Let me see how you discover the problem. I was able to use integral to calculate these kinds of areas which are above the x-axis. Okay, so somehow I am interested in for some reason I'm interested in calculating the area which is below the x-axis. So what do you think I can do? Can I still use integral? Because you know that, I told you that. If you have this situation, the integral is positive. If you have this situation, the integral is negative. And you cannot calculate the integral and say that this area is this integral, because you told me, you convinced me that this integral is negative. And when I say the area is negative, it is nonsense. So, but can you modify it in a way that is still, we can use the idea of integral to calculate the area, even if the area is below the x-axis? Yes?
I mean, if this is the case, that means your integral is going to generate a negative number, which is, I mean, we had our idea that if you have a constant, let's say your constant is -1, you can just pull it out. We can just say that if you have a negative area, you just pull out the negative -1, and then can't you just calculate?
So there is something is missing in your argument.
Okay.
The ideas are not that bad, but you need to tell me why this is the case. Exactly. So let me formulate this, because that is one important part of the lesson, okay? If you, of course, for the exam, you just need to know the information, but I want you to learn why this is true. So my question is this. Consider this scenario. So you have this case, and then here is A, here is B, and this area totally is below the x-axis, let me call it A, and this my function is f of x. So you realize, because of this definition, you know that if I calculate this limit, this integral, I have to calculate this limit. Let me repeat, delta x is positive. For this case, all f values are negative. So each term is negative, negative times positive, negative, and if I add a bunch of negative numbers is negative, and I take the limit, it becomes negative. So, but let me ask you one question. Area is positive, this integral is something that you see here. What is the connection between this number A and that number? What you said, you said what? What is the relation? It's negative. So you said that this integral is negative of A. But we want to justify this idea. So this integral is not A, is negative of A. Okay? In other words, if someone asks you to calculate the area for this case, if you just calculate the integral, that is not correct. You calculate the integral, but you need to multiply it by a negative sign. That is the formula. Okay? This you need to know. Even if you don't like to listen to me why this is true, but this is something that you need to know. But let us understand why this is true. Let me clean this. One way to see this problem is using symmetry. So what we do, I flip this area about the x-axis. So what happens, it means that I will have this scenario, if I can draw it somehow. Yes? So this blue function is not the black function. But if this black function is f of x, what is this blue function? Minus f of x. Yes? And let me call it in my head g of x. And now the point is that this area and that area, how they are related? They are equal. So if this area is A, by flipping it here, that area is still A. Now if I ask you calculate this area, you start from the blue area, which is actually the black area. It becomes equal to the integral of g of x dx from A to, yes? Is that clear? But g of x is negative f of x. So this becomes integral from A to B negative f of x dx. But the meaning of negative of a number means -1 multiplied by that function. Yes? And we just showed that if I have a constant number, I can pull it out. So this -1 can be pulled out. So it becomes -1 multiplied by this number. But usually people don't write -1 times a number. They just simply write minus the number. So that's one way to understand that why this is the case. So remember, there are many problems in the book that you are supposed to calculate the area. Sometimes this area is above the x-axis, sometimes this area is below the x-axis. So if the area is above the x-axis, just calculate the integral. If the area is below the x-axis, what do? You calculate the integral, but remember, by the way, you understand it yourself because it turns out to be negative, it is meaningless. But according to this argument, you have to multiply it by minus sign if you are still interested in calculating the area. So this is important to know, okay? So let me not confuse you. If you want to write something, I would write something here for you. So this is the only important thing. If you're not interested that much to understand the reasons, but so this is the picture that you have to have in mind. So I have this scenario, y is equal to f of x. By the way, I'm always drawing like this. It doesn't matter. So let me just draw a little bit differently. So if you have this function from a to b, and then you are interested in calculating this area, so this area is exactly equal to the integral from a to b f of x dx. But if you have this scenario, so here is a, here is b, and this is your area. The area is not equal to the integral, it is negative of the integral, yes? So this, yeah, just put it in your notebook somewhere that you remember, yes?
Can we take the absolute value of the function and still get the same result? The area.
No, the absolute value, yes, the absolute value is more or less the same thing, it goes up. But calculating the absolute value is not a good idea. The reason is that the primitive function for absolute value is a little bit problematic. Yes. Yeah.
What should we do if the graph has parts that are above envelopes?
Yeah, that's a good question, but I don't know if that's part of your lesson or not, but yeah, we can discuss about that one as well. That's a good question. So let us put it here. So now I see there's some problems there as well. So what happens, so Erasmus is asking what happens if we have both cases in the same problem. But I just want you to understand, if I have this scenario, okay, and here is A, say, and here is B. Okay, and this part, area, I will call it area number 1, and I call this one area number 2, and let us say that this point is also C. Okay, so if I ask you what is the integral from A to B, yes, what is the integral from A to B, and this is my function, f of x dx. How this number, which is a number, how this number is related to A1 and A2. Okay, so you say that I add them up.
Okay, no, not in this case because it's negatives. It's the difference, I guess.
Okay, can I write something here? You mean change it to negative sign?
I mean, this A2 is negative, so I guess, yeah. I guess.
If you really want to understand it, the second one is correct.
Yeah.
Yes, the second one is the correct one. So A1, remember, area by definition is positive. So you calculate this area, But if you add them, these two positive numbers, that positive number is not equal to the integral in the sense of this limit, which is the only sense. That's the only definition, yes? So a1 minus a2 is the correct one. To understand that, of course, it's a little bit technical, okay? But there is a theorem for integrals that if you want to go from integral from a to b f of x dx, you can go from a to c f of x dx, and then from c to b f of x dx. Okay? So this is a theorem that in principle you need to use this definition to prove this. By the way, it's not that hard to see it. If you want to, you can check it yourself, okay? So try to convince yourself, not very rigorously. By the way, what I did is not very rigorous, okay? But that was an intuition behind the proof. So that's also the same thing. So there's a theorem for integrals that if you want to calculate the integral from a to b, you can break it into the middle, you can go up to some point in the middle and then continue. So you can calculate integral from a to b f of x dx. If you want to calculate this, you can go from a to c and then from c to b. Okay, if you agree with this one, then it is not hard. If I ask you what is this one, this is exactly area 1 based on the first picture. Okay, and if I ask you what is the second one, because this second area is below the x-axis, this integral is not exactly area 2, is negative of area 2, and then you can see that's a1 minus a2. Okay? So remember that I think it's good to put this third picture here as well. You just do it yourself. So integral from a to b f of x dx. So let me just draw one more picture here. So if I draw another picture which is consisting of all these cases, so for example, I start from here, go here up to there. Yes, so let me just take it A, take it B, and put this area number 1, area number 2, area number 3, and then of course you can continue. Okay, if I ask you what is the connection between this integral and these areas that you see that this is a1, it's above, minus a2 plus a3, and if there are more terms you can continue. Okay, so be careful. Area and integrals are really close, really related, but you have to be careful about the differences as well. By the way, here, let me ask you a little bit tricky question. Of course, naturally, A is the lower limit, so you expect that A should be smaller than B. But what happens if A is bigger than B? Okay, so some books, by the way, some books take this as a definition, but some books take it and understand it somehow. Can you say if what is my question is that, do you think there is any connection between this integral and the integral in which these limits are flipped? So can you understand somehow by looking at this? So we are training ourselves to understand this definition a little bit better at the level that we can do it in high school, because they are actually quite advanced problems. So what do you think will be the connection between these two integrals in which the role of the limits are actually interchanged? So look at what happens to this limit when I do that change. So the definition is in front of you.
It becomes negative.
Do you agree? Which part affects this one?
Delta x.
Delta x changes. Because you see, if I flip A and B, delta x, the new delta x is not the old delta x. The old delta x is B minus A over n. The new delta x becomes A minus B over n. And these two delta x's differ by a negative sign. So, and that negative sign will go outside. Yes? Is that clear? So that's also another important property of integrals. Yes? Is that clear? Okay. Yeah, I don't want to start the next lesson. Let us stop here. I will continue tomorrow. I want to try to motivate you why the Newton's formula is true next time. Okay, it's probably possible to understand at this level. And then, so this lesson, more or less, except what I have written on the board, is not that important for the exam. So what you need to know from all this lesson for the exam is how to use, if you need to understand these three formulas for the area. Okay, later I tell you how to calculate this integral, not from this definition, because I gave you one example for the very simple function. It was very lengthy, and for most of the function it is impossible at all. So then I will tell you how to calculate this integral. I will try to motivate you why that method is working, not the real proof, but you can see why this formula should be true. Any questions? Thank you very much.